Alright, that'll do it. I will begin with a word of prayer. Right after I move this microwave. You didn't see that coming, did you? There, better. Right. Heavenly Father, we thank you for this day. I just pray that you help us to use this time wisely, just to learn what we need to about homotopy and cones and such. And, I pray, Lord Jesus. Amen. So let me get back into it. So, we've gotten to the point of talking about the problem of extending a map, right? So, you have a map F from a space X to a space Z, and draw a picture like this. Here's your X, here's your Z, here's your map F, right? And you've got some larger space Y, right? And X is included in there. And the question is, how do you get this extension up here to G, right? He says homotopy itself raises such a problem, right? Because to show F naught is homotopic to F1, we can do that if we can extend, right? Think about that. F naught homotopic to F1 means can extend what? F naught union F1, right? From X across the 0 point set union with X across the 1 point set to Z, right? To all of X, right? So they basically think this you want to extend to X across the whole unit interval, right? So this is playing the role of X over here, right? And this is playing the role of Y in the diagram. So I suppose I mean, is it fair to say that if F naught is not homotopic to F1, such an extension can't exist? At least not a continuous extension.
Well, you mean of
there more data?
This particular form, you mean?
But is there more data? Is it, I mean... Yeah, I mean, let's see, all that a homotopy is it's a continuous mapping from X cross I, right? That agrees on the endpoints, right? Time 0 and time 1. Time 0 and time 1, it reduces to the F naught and F1. Yeah. Oh, sorry. So theorem. Let me not waste our time away with uninteresting questions. Let's see here. So a theorem. It's theorem 1.6. Again, this is on page 17 of Rotman. Let F from the n sphere to Y be continuous, and the following are equivalent. One, F is null homotopic. In other words, what? It's homotopic to a constant map, right? It's null homotopic. Two, F can be extended. Let's say it's extendable. F is extendable to continuous map from the n+1 disk to y, right? Or 3, a slightly more technical condition, if x naught is an element of the n sphere, and k is a constant map from the n sphere to y at f of x naught, then there exists homotopy f, which shows that f is homotopic to k with f of x naught comma t equal to f of x naught excuse me, for all t in the interval I. Okay. Excuse me. All right. This is my favorite part of this class. Sitting down in a comfortable chair. Ooh. Dizzy. So here. Clip this. Should we give him a name?
Turtle Man.
Turtle Man.
Looks more like a giraffe man to me.
The Giraffe Man. Yes. Yes. Thanks to Justin Cooper for creating that. Should give credit where credit's due. Oh, Nathan. I'm not sure, but these might be. You should check on whether or not those belong to the same homework that you have there.
Math 421.
Yeah, I know. The question is, are they the same set? There's I forget which one I gave you. Is it lecture 2 homework, or is it?
Oh.
I think you have lecture 2 homework. If those either of those are lecture 2, then you should take them.
This says homework 3.
Homework 3, that's mine.
And this one says lecture 4.
That one's mine. Okay, so you can just set on my desk. I'll lose them. Okay, so let's look at the proof just to get started here. So to prove 1 implies 2, how do we do that? So we should assume what? F is no homotopic, right? So F is homotopic to C, where C is the constant map, right? Constant map from where to where?
Sn to y.
Sn to y, right. Excuse me. And in particular, we'll let C of x equal to y naught for all x in Sn, just to make it, to be precise. Then what do we do? I guess we have to, we're trying to,
Extend that.
yeah, we're trying to extend f to dn plus 1. Let's see here. So, like, roughly speaking, a picture of what's going on is what? So it's something like this, right? This is Sn. And the dn plus 1 is in here, right? So, for example, S1 is the circle, D2 is the disk. So we need to define the let's call the extension G. We want to define G of x equal to, so, whoa.
Yeah.
What the what?
This first implication is not intuitive at all.
Huh. So he lets it be why not? I mean, why not? If 0 less than or equal to the length of x less than or equal to a half. So basically if you're in here, right, he's got y naught for those places. Oh, I guess it's not dotted, right? And then he uses the okay. So the homotopy exists, right? So we know use the homotopy. The homotopy which does what? The homotopy which shows that f is homotopic to c. So he does f of what's he got here? X divided by the length of x. All right, comma 2 minus 2 times the norm of x. And that's if 1/2 is less than or equal to the norm of x is less than or equal to 1. Oops, sorry. Excuse me. Each piece is clearly continuous, right? The constant map is continuous, and we're looking at a homotopy, which is continuous, but the inputs to the homotopy, you might worry about division by 0 here, except it doesn't happen. So that's continuous, composition of continuous. Each piece is separately continuous. We should worry, does it glue, right? The join, when you get to, you might worry about x such that the length of x is a half, right? Distance, circle, radius half from the origin. I guess sphere, technically, right? So what happens when you put length of x equal to a half here?
You get f of like the projection of x onto the Sn. I mean, if you call it projection.
So we get f of 1/2, comma, this is what, at 1/2?
We shouldn't
Wait, no,
be
but f
1.
of 2x.
No, this is 1/2, because if I have,
Oh, you're dividing.
I'm looking at this,
Yeah.
that's 1. The point is that f is a homotopy. It doesn't matter what's here. This is equal to, right, the constant at 1/2, constant map at 1/2, which of course is just y naught. I shouldn't really be using this marker. No one can see this. It's like I'm writing nothing on the board right now.
You can see some stuff.
Oh, really?
Maybe not too clear.
All right, well, they'll figure it out. The point is if you plug a half into the homotopy,
Well, it should be an element of S.
oh,
So
Yeah,
it's
so
x. It's 2x.
aw, man.
Whatever x is.
Oh, 2x. I'm sorry. You guys are right. Thank you. Is that right?
Yeah, and 2x is an element of Sn. Since the norm of x is a half.
Is that right?
Shouldn't be x over 2 though.
No, you're dividing by 1/2.
Oh, right. Yeah, I think that's right.
2x is an element of... You sure 2x is an element of...
If the norm of x is 1/2, the norm of 2x would be 1. So it would
Oh,
be on the
okay.
sphere.
Very good. Very good. Oh, that's why that's done. That makes sense, right?
To get
Okay,
an
that makes
element.
perfect sense now that I think about it. Okay. So, this is an element of Sn. Yeah. I mean, more to the point, that's an element of Sn, so I mean, this is actually a well-defined map.
Mhm.
Otherwise, we'd be in trouble. So we should talk about that. Anyway, the point is, when you look at the norm of x equal to a half, we get y naught here. Of course, in the other case, we have y naught, so they match on the where they're glued together. So by the gluing lemma, it's continuous. And of course, you can also see that if you look at G restricting, right, the restriction of G to Sn, what do you get? You get back your map F, right? So G is an extension of F, right? And these cases comprise dn, right? dn plus 1, so. All right. Excuse me. Can I erase this?
Yeah.
So to let's see here, 2 implies 3. We assume f is extendable. Right. In particular, G restricted to Sn is equal to f, and G is a mapping from dn plus 1 to y continuous, right? That's what we're saying. We're assuming that much. There exists this map G, right? So what do we, to prove 3, what do I have to do? I suppose I should let x not be an element of Sn, right? And I should probably suppose k is a map from Sn to y, right? Is k a constant map?
Yeah. Its value is f of x naught.
Okay, so constant with k of x equal to f of x naught. So I have to, all that remains then is to construct the homotopy, right? So we need to construct a homotopy that shows that f is homotopic to k, and also that the homotopy has this condition. So the difference, guys, the difference between this and other homotopies is that usually the homotopy says something about t equals 0 and t equals 1, right? This one stays at f of x naught from t equals 0 to all the way to 1, everywhere in between too, It's kind of a rather
Just
boring.
a little bit more information.
Yeah, it's kind of special homotopy, exactly. So here's what he says. He says you define it by setting f of x comma t equal to, he uses g of 1 minus t, right, times x plus tx naught. Let's see here. Let's think about this. So like here, where is x?
In Sn.
So like x an element of Sn? So that makes x like here, right? And x
X naught is going to be fixed.
oh, x naught's also an element of Sn, so it's like over here, right? And then so this is the line at t equals to 1, it's at x naught. T equals to 0, it's at x, right? So that's basically the line that goes from there to there. And like here, it would be, say, gamma of t, if I call this whole thing gamma. So it's fairly clear that we're not misbehaving, right? We're in dn plus 1. So g of that quantity makes sense. So then what?
You can check if it's homotopy.
check that it's a homotopy? Yeah. He says visibly, f is continuous. Clearly, f continuous.
I mean, it's true.
Yeah, it is the composite of a parameterized line and a continuous given continuous function. So yeah, it's continuous. And then of course we need what, f of x comma 0.
It's just going to be g of x,
Right.
which is f of x.
Oh, right.
So
Okay.
it's g restricted, yeah.
That's for x at Sn, of course, right? Excuse me. And f of x1 is what? No, g of x naught. Right. Which is f of x naught. Where did we use k?
I mean, k is what maps to f of x naught. So, I mean, f of x naught is k of x for all x. So I guess we should put that.
So this is equal to k of x naught, yeah. Well, this is
K of x.
k of x, right? So that shows that f is a homotopy of f and k, right? Did we get that condition up there yet?
No.
Oh, I guess we just, but that's probably just plug it in, pops out.
Yeah.
Yeah.
So you guys already see it. I'm closer to the board, it's harder for me to see. See your x naught, so I plug in x naught.
You get one.
that's g of x naught, okay. Alright, yeah. Because these just cancel. Cool. Yeah. Alright. I will leave the proof of 3 implies 1 to you guys. See here.
Can that be a homework problem?
Oh yeah, that's funny. That is, it really is obvious. Okay. All right. He says, compare this theorem with lemma point 2. If y is equal to Sn and f is the identity, then lemma point 2, not yet officially known, implies that f is not holotopic. I can't say words. F is not null homotopic. Otherwise, Sn would be a retractive Gn plus 1. All right. Let me erase all this. Time for cones.
Cones.
All right. Probably Angry Birds. Yeah. All right. Stupid Angry Bird. How about I stop the Angry Bird texts? You know?
I actually sent you texts.
Yes.
That's horrible.
What? You should just block the number.
I know. All right. Definition. So
Did you
here.
sign up for something? Or
Not really. I mean, I just didn't. You know, I want the Angry Birds on my phone for the kids to kill the pigs, you know? So this again is, you know, page 18, Robin. All right. So definition, a subset X of Rm is convex if for each pair of points x and y and x, the line segment joining x and y is contained in x. So here I'll just make a picture. This is not convex because, as you can see, the line segment joining this point x and this point y has points like z, which are not an element of S, right? In contrast, something like this is convex because, as you can see, if you take the point x and the point y, every point in between, like this, x plus t times y minus x is an element of, let me call this thing big T. For all t in 0, 1. So if all line segments between points of a subset of Rm are contained in the set, it's said to be convex. We've talked about this before. There you go. Definition. A space X is contractible. It's contractible is contractible if what? The identity on the space, right, is null homotopic. Now, at first glance, that doesn't look much like the definition of contractible I gave in previous course. Like, what did I say contractible was? Or did I say this?
I don't remember.
Did not say
It was,
This is the same homotopy type as a point.
Oh, I can say the same.
I don't know.
I sometimes say it's contractible if you can shrink loops.
Oh yeah.
Yeah.
To a point.
I said that.
Yeah. This is really just a fancy way of saying that. So here's the theorem. A space, every convex set is contractible. Now, I think we've only defined convex set in the concept. I mean, these.
All right.
Yeah, these are both inside in the universe of Rm, right? So, all right. So here's the proof. So he says, choose. So let x be convex, right? You didn't say that, but I'll say that. Let x be convex, right? Choose x not an element of x, right? So let's see here. Man, I still think I am missing something. Why is that not convex? It's convex. So as I pick x naught, right? And then what's he do? He says define C C of x equals to x naught, right? For all x in x. And then what's the homotopy? Let f of x comma t equal to tx naught, right, plus 1 minus t times x. So let's see here. I mean, it's got to be some picture to draw to explain what he's doing. But anyway, so does it work? I mean, this is continuous, right?
Yeah.
When we put t equal to 0, we get what?
The identity function. You just get x.
Get x back, all right.
Oh, I just realized you said a hemisphere, not a like hemidisc. So like a hemisphere would be like half circle, right? And that's not convex.
Oh,
Yeah.
so it's like a half circle.
Yeah,
Oh.
that makes so much more sense.
Oh my goodness. Okay, or one of these guys.
Yeah, exactly.
Oh, absolutely. That's right. In fact, it's kind of maximally not convex. It's sort of like maximally unconvex in some
Yeah.
sense, right? Because only the endpoints of the stupid line segment are on the. What's that called? It's got to be some name. I mean, this is like the farthest from convex you can be, right? Maximally unconvex.
Absolutely convex.
Absolutely unconvex. Anyway, this is of course the identity on x of x, right? And then, oh, thank you, Daniel. I feel much better now. The burden has been lifted off my shoulders. I say fx1 is what? That's just x naught, right? And of course that's c of x. So therefore f is showing that the identity map on x is homotopic, the constant map. Behave. Stupid marker. Ah, hemisphere. Man, not a hemidisc or a what's it? What's it?
Handball.
Half disc or a half ball. Embarrassing. All right. Well, I feel much better. Thank you. The coming construction of cone. All right. Will show that every space can be embedded in a contractible space. Before giving the definition, let us recall the construction of a quotient space. Actually, let's not. Let me just read it. Now, what he says here is interesting, though. Like, his description of quotient space is very useful. Basically, you have topological space, you have a partition of it into these pairwise disjoint sets. Then x prime being the partition, right? He says a natural map from the space to the x prime, the set of disjoint sets, right, is just defined by v of x equals to xj, where xj is the unique subset of the partition containing x, right? So I can draw a picture for that, actually. It might be useful. So here's your space, x, right? And over here is your space x prime, right? But x prime isn't the space anymore, it's... My picture doesn't do it justice, of course. These are disjoint, right? So imagine that each one of these edges is taken by just one of the sets and not more than one. And imagine that these are the same shape. And anyway, so the natural map, as he says, nu. So basically, if you were to look at over here, anything in here, all these points, all these different points, right? they all get mapped to this one element over here. So in X prime, the elements are sets. Right? So basically everything in this region is getting squished to this one single object over here by the natural map. So the quotient topology on X prime is the family of all subsets U prime of X such that the inverse image of the natural map is open in X. Among other things, this makes this a continuous map. Now, here's the comment he makes next. I really, really appreciate it. He says there are two special cases we wish to mention. First of all, if A is a subset of X, right, then we write, so if, two cases to consider, if A is a subset of X, right, then for X prime, we usually write X mod A. And the partition done for that is you take A, that's one of the things in the family of disjoint sets, and then every other point in X outside of A, you just make singletons. And so basically what this is doing is it's just squashing A to a point in the quotient, and all of the other points are left alone. They still exist, right? That's one notion, of course, of quotient. But he said, on the other hand, that differs from the quotient group construction, right? If A is a normal subgroup. So there, the second special case arises from equivalence relation on X. In this case, the partition consists of all equivalence classes. The natural map is given by X maps to the equivalence class of X. And so there, of course, it's more like the pictures we see in group theory books, right? All points are messed with, but in a systematic way, right? We look at the cosets as points in the new space. All right. At this point, he gives some standard examples about, taking the unit interval and identifying the endpoints. Gives you a circle, right? If you take a rectangle and you identify the line segments in the same way, we get a cylinder. If you take the cylinder and you identify the end circles in the same way, you get a torus, right? Or we could make a Mobius strip, and so forth and so on.
Yeah, I'm
all right. But you guys have seen these things before, so I'm not gonna. All right. What's an identification?
It's a continuous surjection such that the inverse, a set is open if and only if the inverse image of, or I guess a set
That's
in,
it?
a set in the
That's it.
domain is open if and only if it's the inverse image of a set in the range, right? Or is that not quite right?
Other way around.
Other way
They said,
around?
well, I think you meant what you. I think you were thinking what I heard you say was domain. What you meant was range. A set in the range is open only if its inverse image is
Okay.
open. That makes it an identification.
Yeah, that makes sense too, because like it's sort of analogous to the nu in the quotient construction.
Right. Yeah. For example.
So that's exactly how the open sets are defined in the quotient. So.
Yeah, the natural map is an identification in the quotient, right? This example 1.3 is very nice, right? He mentions if you just have a function, right, you can get an equivalence relation by the fibers in the domain, and so that allows you to construct a quotient space by X mod the kernel of a map, and that's that's a set theoretic kernel, right? So that's a very general. Mentions he gives you this little diagram, right? I think he'll come back to this, so I'm mentioning it. So like X mapping to Y, H, right? Then the natural map, and this is not this kind of one, right? This is more of the group theoretic type, right? Because this squashes fibers to points, right? So I guess it depends on the nature of the map H to be careful, but for a lot of functions, this is gonna mess with a lot of points, I think, right? I'm trying to think. What would it take for...
I think one of the later theorems shows that the notions are essentially the same up to homeomorphism. So you can always find a map whose kernel will be homeomorphic to like the standard quotient construction.
Oh, okay.
If I'm interpreting it right, but I think it says it in there.
Huh. So he talks here about section. What is a section, right? What's a fiber, right? So I think we know a little bit about what those are. I'm gonna move along here. All right, sorry, I'm trying. I want to get to the meat here. I mean, these things I think we went through last semester, at least partially. You know, theorems about identifications, fibers, sections, how that all relates. So I'll just let you read page 21, 22. Cone is what I wanted to get to. All right, so cone. Excuse me, guys. I mean, let's be realistic. If I really get into, and we know already, if I just try to talk about quotient topology, identifications, and all of that, that's an hour-and-a-half discussion. We've done that before. Ay, ay, ay. Cone. Why didn't I erase this? X a space. Define equivalence relation on X Cartesian product of the unit interval by X comma T, all right, is equivalent to X prime T prime if T equals to T prime equals to 1. We'll denote the equivalence class of X comma T by this. In other words, this is equal to, but we take no joy in writing double brackets, so the cone over X is called Cx, and it is the quotient. It's the quotient space X cross I mod this equivalence. So I got to draw some pictures. So of course, you guys know we have a circle, right? Like S, right? S1. Draw another circle over here, S1. Well, S1 cross I, that's easy enough to picture, right? So like S1 cross I guess there's different ways you could attach I, but you could attach it like this, right? If I'd done this right, you know, it would be like vertical, right? And so like S1 cross I is what? It's like, it's a cylinder, right? if you take that, right, and you say all the, so this, the top rim is basically, here's your t equals to 1, right, on the top, right? So you take that and you glue those together, right? Glue these together to a point, and that's why this is called a cone, right? So this is, you know, S1 cross I mod that equivalence. So the, what is that point at the top called?
Vertex.
Yeah, the vertex. And so what he says is we have essentially introduced a new point in V, which was not in X, and we've joined each point in X to V by a line segment.
Does it have to be a line segment? Okay.
Well, I mean, what's a line segment?
Yeah, I think so.
If a line segment is, I mean, you fix a point in X and you let t vary from 0 to 1. If you're willing to say that's a line segment, then it's a line segment.
Okay.
So, like Professor Smith in Calc 3, he defined a line. Here's how he defined line in Calc 3. I thought it was kind of cute and really kind of fun. So he says, you know what his definition for line is? Because he asked them to prove that the parametric form of a line was a line, which to me is kind of like, because for me I used the parametric form of a line to define a line in Calc 3 for pragmatical purposes. But his definition of a line is it's a set such that if you take any three points, then the distance from one to the other plus the distance from the other to the one is equal to the distance from the, you know, so you can sort the 3 points such that the distances add up. He may have had a slightly more careful way to say it, he probably did, but I thought, oh, it's kind of geometrically reasonable and like a primordial definition to make Calculus 3 students suffer with to start with. But so it's interesting, I don't know. It's interesting to see what happens when you have like an original thinker teach something like Calculus 3 for the first time, like the kind of things they think of. Because they don't, you know, a person who's a real mathematician won't look at a textbook, they'll just think. And what they come up with may or may not have any resemblance to the text. I, on the other hand, I'm more a creature of habit and tradition. Alright, anyway. Where was I? Oh, he warns that the picture is fine when X is compact Hausdorff, but it may be misleading otherwise. He says the quotient topology may have more open sets than expected. He then gives a example down at the bottom. I need to get a copy of Dugunji. And also the other one he mentions, Dunford and Schwartz. I need to get a copy of those. I'm sitting around here. I bet that's this Schwartz who did the like the direct delta function. I don't know. I'll look into this. Oh, again, when I teach math history, I'll figure it out. Let's see. What's his next example? First base is x and y. Let's see here. Oh, he proves that dn plus 1 is the cone over Sn with vertex 0. Let me read that again. dn plus 1 is the cone over Sn with vertex 0. So, as far as topology is concerned, you can see how this green space is the same as this one, right? So, like, the origin is the vertex, yeah. But he gives us explicit formulas in example 1.7 to prove that, right? So, actually, he does something more general, doesn't he? I better write that out. It's like if you take f continuous from x cross I, right, to y, and suppose f of x comma 1 equals y naught, and it says, you know, for all x in x, and he says that induces a continuous map from where to where? From the cone of x to y. How so? By what? So if you feed it the equivalence class of xt, what do you give it? What do you excuse me. You just f of xt. So keep in mind that this is continuous, right? But we're not really saying much about it except that it's continuous on this Cartesian product. And by the way, this value, it happens to be constant on 1. So as x varies, but t is fixed at 1, it's constant, why not? Otherwise, it's continuous, who cares, whatever. So given that, we can induce rather. It's not an extension, is it? I mean, this, we're looking at the quotient of that, right, by the equivalence, by the cone equivalence. And so does this make sense to you guys?
Yeah.
I think so.
I mean, because it's well defined, because you have that. I mean, that's pretty much all you need to know.
Right, otherwise we'd be worried that it wasn't single valued, right? Because if like, so yeah. Okay, so then what? He's like, if you let, so he says, for example, you look at f from the n sphere across the interval, right? To dn plus 1, defined how so? He says take the map u comma t and map to, he says 1 minus t times u. Let me try to picture that. So here's my picture of that, right? And my picture of this is basically, okay, so I take so 1 minus t, so it's something like
It's like that far into the disk.
yeah, exactly. So like here's u out here, right? And then it tracks like, it's like here or something like that. Right? So it's almost, it's really what's, if you can imagine it, it's exactly taking the cylinder and like just lying it down on the disk. Right? And of course,
And that induces.
they all end up intersecting in the middle at the origin. But you can check, of course, that f of u comma 1 is equal to what?
0.
Right, 0 for all u and Sn. So that's a continuous map. And then the f bar, you know, as he says the reader may check that f bar is a homeomorphism. it's pretty clear that so f bar, what is f bar? F bar.
It's induced map.
Yes.
I mean, I think you could argue, like, it's pretty easy to see how you could define an inverse map, right?
Yeah.
Because, I mean, you know, each element of the disk has a unique polar form representation.
Yeah.
So you use that to get the inverse, you know, returning, you know,
Yeah. It's a
the
pretty
direction on the circle, and then T is the radius.
right. Cool. So let's see here. Then our next move is to do what? Theorem 1.11. Ooh, I like that proof of this theorem. Look at that thing. Theorem 1.11. For every space X, the cone CX is contractible. Can we prove that? Proof. Let us try to understand this one-line proof. Define f that goes from the cone over x across the unit interval to the cone over x by f of equivalence class x comma d s equals to the equivalence class of x comma 1 minus s times t plus s. All right. Now, what was the theorem we had? Or what was the definition of contractible we had? Is null homotopic? If the identity map was null homotopic, right? So hopefully this shows that the identity map on CX, right, is homotopic to what? Constant map. If I had to guess,
That's the vertex.
the vertex. Yeah, at the vertex. I mean, if it's not the vertex, I will be shocked. All right, so let's check it out. F of x comma t 0 is what?
X
Just X come to.
X comma t. Well, that indeedly doodly, that does look like the identity. So there's your identity. And how about 1?
It's gonna be X comma 1.
Man, I'm glad I'm not taking a class. You know, this would be terrifying to take as a class. I would have so many stupid little formulas to remember. Like, these things are all pretty easy to prove if you can write this down.
Yeah.
But how do you cook that thing up, you know?
I mean, I guess if you were like saying, wanted to show it was homotopic to the constant function that maps to the vertex, it might not be too hard to construct.
Hmm.
It's probably hard.
Yeah, I'm sorry, I lost my way.